Aidan, and the title is translated from something. We are back again. Wait,
There's more to it, but that'll do. Thank you. Yeah, well, actually, it's Tolkien. Yeah, okay. So I guess I'm going to try and be relatively quick. Maybe I'll see if I can get us to the hub a little bit earlier. And what I wanted to do, I'm not going to really do anything very technical, and I'm not really going to state, we're certainly going to state any theorems of mine. We're going to talk about just a general idea that has to do with the sorts of C-star algebras we've been talking about today. Also why, so if you, the way I see things anyway, I come to Western Sydney University, if you see a title that says C-star algebras, you usually pick up at the algebras bit, maybe not at the C-star bit. So I'm going to try and sort of say something about connections with algebra. And I always think of this quote that Bruce pointed out to me of Berberian in one of his books, where he says, you know, when all of the functional analysis is stripped away, you should still have a solid piece of algebra that explains what's going on. So I'm going to try and give that picture for what is going on with these groupoids. So I guess, say I start by writing C-star algebras. All right, well, in this room you might ask, why? And my answer to that is because quantum. Okay, so if you want to model what happens when you've got a photon moving on a line, so you've only got one dimension to work with, right? So there's really only two things you can measure. You can measure how fast it's moving, and you can measure how much volume, you mention where it is and how fast it's going, position and momentum. All right. You try and, so I guess Heisenberg was doing things like this back in the 1920s, that you wrote down what's going on, and it's really weird. And it turns out the way that you model this is with two operators that satisfy what are called the canonical commutation relations. And you work out what the solutions to those can be, and there are no finite dimensional solutions. They have to live on an infinite dimensional Hilbert space, even after you make them bounded. And you're stuck with C-star algebras. So you're stuck with norm-bounded collections of bounded linear operators. Okay, so why quantum? All right, well, if we've decided we need to know about C-star algebras, so we've answered why, then the next question is what the hell are C-star algebras? And that's what I'm going to try and say something about. So there's a lie that we tell. It's not really a lie, but it's one of these things that, you know, it's, so I'll say, so they're things that are closed bounded subalgebras of the bounded operators on Hilbert space, closed star subalgebras, bounded operators on Hilbert space. Okay, it's not really a lie. It's kind of, it's true, but it's got about the same amount of descriptive power as if I say a group is a collection of bijections of a set that is closed under inverses and opposition. But it's true, every group does look like that, but the set's really getting in the way. That's not what a group is, right? What we really want is some sort of abstract description that describes it intrinsically. And it's even worse when I say this, when I use this formulation of what a C-star algebra is than it is for a group. Because at least with a group, when I write down the obvious way that a group acts on a set, it acts freely and transitively. Like the set basically looks like the group. When I do the construction that you use to say that a C-star algebra looks like this, you wind up with an absolute mess. Right? So that the thing that you wind up representing on is way bigger than it needs to be. I'll give you an example. So if I take the C-star algebra of the group of integers. So by that I mean I want to take a unitary representation of the integer group. Well, if I want a representation of the integer group, I only need one thing, right? So I've got a unitary, basically. All right. So what do I get if I apply the theorem that says that every C-star algebra is bounded operators on Hilbert space to this example? Well, the space that I would wind up with, if I did this, even if I restricted myself to just the pure states in the GNS construction, which I might not, but the Hilbert space would wind up being the little L2 space of the unit circle. Here the unit circle is discrete. So this is a non-separable infinite dimensional Hilbert space. I've completely lost the topology or anything to do with the structure of the group. And I don't even know which I mean, it's some of the operators on this Hilbert space, but it's certainly not all of them, because the operators that are allowed are diagonal operators that are continuous with respect to points in the circle, but I've forgotten the topology, all right? So this GNS representation is just way less efficient than it should be. That's the wrong representation, right? Why is it the wrong representation? So if I want to say, you know, if my honors student gives me this representation, I don't give them very many marks. And I say, no, that's not the representation you should have given me. The representation you should have given me is this. So this is a commutative C-star algebra, and there's another theorem about commutative C-star algebras. So commutative, the C-star algebra, so A is going to be, and I'll not worry about compact and non-compact, it looks like continuous functions on its character space. And by characters, I just mean homomorphisms into the complex numbers. So commutative C-star algebra allows homomorphisms into complex numbers. What does the homomorphism into the complex numbers look like here? Well, again, this is generated by one thing, a unitary, right? So I've got to assign a number to a unitary. If it's going to be a representation, that number better be at modulus 1 because it should be equal to its own adjoint. Okay, and it should be, its inverse should be its adjoint. And so I've got a point on the unit circle, but now I've got the continuous functions on the circle. Oh, well, that's much better. I'm not realizing it as a bunch of operators on Hilbert space anymore, but I am realizing it as continuous functions on the circle, which is exactly what it should be. And like I really can see the topology and everything there. Right? So this is a much better picture for the C-star algebra business.
You just put it on real L2.
Yeah, so then it would be on capital L2, right? And the point is, what am I getting here? I'm just getting Pontryagin duality back, right? So we know this. This is a better picture. Let me give you another example. So if I take the C-star algebra that's generated by, we've seen this one already, two elements, S1 and S2, and I ask that S1 star equals S1 equals S2 star S2 equals the identity, and S1 star plus S2 star is the identity. So I've got two isometries on here. We've got two isometries, and the ranges are orthogonal and add up to the whole space, right? All right, so it turns out there's only one C-star algebra that you can get satisfying these relations. So only if you take any two operators with this property, you'll always get a copy of the same C-star algebra. But what happens if you do this to it? When I do this to it, it contains as a very, very small, so via GNS, the Hilbert space contains as a very small, like it's really small, subset, something like little L2 of all the pairs that look like this, maybe a mu x, I probably have to put an n here, so mod mu minus mod mu x. Mu and mu are in finite strings of 0, 1, and x is an infinite string of zeros and ones. Again, with no topology, because the GNS construction doesn't do that. Which is, again, a huge non-separable Hilbert space and certainly way more complicated than it needs to be. There's a lot of redundancy because all that these operators are doing are either appending a 0 or a 1 to the mu. They don't even see the mu. They don't care about this number very much when they adjust it, but most of this is just redundant information that comes out of the GNS construction. Okay, so what I'm trying to argue is, yes, it's true that every C-star algebra is a bunch of bounded operators, operators on Hilbert space, but that's not really the way to think about it. So what we want to do instead is think about them in terms of dynamics on spaces. Okay, so I guess my point is there's an obvious way better way to do this, right? Just take little L2 of the natural numbers. One of the operators sends every number n to 2n plus 1 and the other one sends it to 2n. That's if I wanted to take an infinite set and write it as twice itself, that's how I do it, right? So there's an obvious way to do it, and it's not the way that comes out of the GNS construction. All good? Okay. So that's a bit of a mess, and we want a better way to think of at least some C-star algebras. So what we're looking for is C-star algebras where there's a nicer picture. Sorry, double drop. Okay. So what do we do instead? Well, what we do is we characterize, so instead, we axiomatize, right? Just like you would with a group, you write down some axioms that describe the thing you're interested in. For C-star algebra, there's a list of axioms, and I'm not going to write them down because it doesn't matter. And then look for models. Right? And the model that I'm going to talk about today is the groupoids that we've heard about a few times. And I'm just going to try to show you why I think they're a particularly natural way to think about this. Okay. So I guess the starting point is that, and I already said something about it. So for commutative C-star algebras, we have a good model. Right? That's this one. Okay. So I'm going to try to leverage that as much as I possibly can to understand more general C-star algebras. That's my starting point. And now I want to say, suppose I've got an arbitrary C-star algebra, how can I try to leverage this? How can I use this as much as possible? And the trick is I'm going to use, and this is why I say it sort of links to algebra, I'm going to use just a very sort of basic idea behind Morita equivalence theory for algebras to try to realize more complicated C-star algebras in terms of dynamics based on this. So, so let me give you an example of where this theorem is useful inside an arbitrary general C-star algebra that is not necessarily. So, example, say I've got some big C-star algebra A, and then I've got B one. And I'll ask one thing from it. I'll ask that. I ask that I'm going to want A to commute. No, actually, I don't even need that. Forget it. I just take the element A and A. Then A star A and A star. Well, those are also elements of the C-star algebra, right? And they clearly commute with themselves. I mean, everything commutes with itself. And they're self-adjoint. Yep. So they generate commutative C-star subalgebras. These generate commutative subalgebras, which I'll write as C star of A star A and C star of A star. So those two things are functions on some space. All right. Now, if I were trying to relate the representation theory of two algebras, I would look for a Morita context between them, right? I'd look for a pair of modules R and S. So one's a this, that module, and the other one's a that, this module. And when I test them in the two possible orders, I get the two possible algebras, right? Okay. For C-star algebras, there's a notion of Morita equivalence. I guess it's sometimes called Riefel Morita equivalence because Mark Riefel developed it. And it turns out that for C-star algebras, you don't really need two modules, R and S. You need a single module, but it's an inner product module. So it has a natural adjoint module. And so that it's like the R, but there's automatically an S, and you don't really get any choice in what it is, right? So given it's called a imprimitivity module. X from A to B, I get irreducibles of A in bijection with irreducibles of B. This is for a favorite pair of C-star algebras. And if A and B are abelian C-star algebras, the reason this works is because the irreducible representations are one-dimensional representations. So this becomes, so if A and B are abelian, what this is a homeomorphism between representation spaces, but it becomes a homeomorphism between these dual spaces, right? Just inducing one-dimensional representations. All right. So in particular, if I've got a Merida equivalence module between the C-star algebra generated by AA star and the C-star algebra generated by A star A, I'll get a nice little bit of dynamics. Where would I get such a bimodule? Well, it's not too hard to imagine how to build a bimodule between those two algebras. I'll do this. I'll take A and multiply it on the left, by C-star of A star, or, as it turns out, on the right, by C-star of A star A, and I will get the same thing either way, and it will be a Merida equivalence bimodule between those two C-star algebras. And so it will always give me a homeomorphism, which I'll call alpha A, from from A star A hat to A star A. Okay, great. That was just for an arbitrary element of the C-star algebra. So what does that say? It sort of says that if I pick out an element of a C-star algebra, what I've really got is two little bits of topological space and a homeomorphism connecting them. But I don't really want to deal with one element of a C-star algebra at a time. I want to glue all this together into something global. So the picture I'm looking for is something like this. So let me just go back to our starting point. A C-star algebra was a bunch of bounded operators on a Hilbert space. When I think of a bounded operator on a Hilbert space, I think of something that looks like this. So I've got some entries here that might be called AXX, and over here I might have an AXY, and down here I might have an AYX, and it would be some very big matrix, right? Yeah. So I've got some diagonal thing and then off diagonal coordinates. So the problem is when I go to the GNS, use the GNS construction to realize things on Hilbert space, I don't get all possible matrices. Maybe I don't get any rank 1 projections. Maybe I don't get, maybe there's a sort of a strong connection between what the numbers on the diagonal have to be and so forth, as in the C or T example. So this isn't going to work. But I still want a picture that looks a bit like that. It's just that now what I want to do is take my elements A in the C-star algebra and think of them as little tubes of arrows between bits of some diagonal space that goes down the middle. Yeah. I'm lying a little bit because it's not really true that the spectrum of A star and the spectrum of AA star are subsets of this thing. They're going to sort of be glued into it via some topological process. They're all going to get mushed together. But roughly speaking, that's what I want things to look like locally. And the question is, basically, when does this work? Like, can we actually make that happen? And so, great, we want it to look like that. Can we make it look like that? Well, there's a couple of issues. Firstly, I'm going to need to make sure that when I take all of these different A star A things, see, if I want to get a space here, I want whatever goes here, I want it to be a capital A hat for some C star algebra capital A. The way that I do that is by basically fixing that in advance. So the idea is we look for an abelian or a commutative, let's call it D, a diagonal, take it A, right? And now I only, and just consider the elements in A, so these are going to be my A's, such that N to the N star and N star to the N, I can take it D. And the point is, if I make sure that B is big, say it has an approximate unity, that's going to guarantee that N star N and N star are both in D. Since D is abelian, that means all of these things commute with each other, these N stars and N stars. So I get a big global commutative C star algebra that these are sort of locally dynamic. Yeah. All right, but there's another complication, and that is that we can't really expect this to work just as it stands. Because, for example, if I take just C-star algebras whose irreducible representations always look like a copy of the compact operators. So these are called type 1 C-star algebras. If I just look at type 1 C-star algebras, so problem, even for the easy, I say that in quotes because they're not easy at all, it's just they're old, and so we pretend that they're easy because people figured it out a long time ago. Type 1 C-star algebras. There's an obstruction to this local model patching into a global. Right? We sort of know to expect this. Locally trivial things are not usually globally trivial. Right? We've locally trivialized something. We've locally looked at what it is. We said locally this looks like some dynamics on the space, but globally it probably doesn't, right? And we're used to the idea just from algebraic topology that locally trivial things are not locally trivial. That's exactly what algebraic topology does, right? So the obstruction, or one obstruction, is isomorphism classes of vector bundles. Well, let's go right back to Rosie and think about obstructions to, locally trivial becoming globally trivial. I look at what the possible isomorphism classes of vector bundles are. That's the way to distinguish them. Okay, so I'm expecting to see some vector bundles showing up here, or I would maybe like to see some vector bundles showing up here. And the cool thing is, they already have. So I emphasized over here that every time I've got an element A, I get a Merida equivalence by module, and that gave me a reequilibrium. But it gives me a little bit more than that, because any time I've got an Merida equivalence by module between commutative C-star algebras, like I said, that means it has to induce one-dimensional representations to one-dimensional representations. A Merida equivalence, well, any Hilbert module whose right algebra is commutative, it's always going to decompose as a field of vector spaces. Yeah. And when I induce a representation from right to left, what's going to happen to its dimension is it will be multiplied by the dimension of the fiber of the module that I'm using. So the general principle is that So the general principle is anytime I've got something like this and B is commutative, I've got a bundle of Hilbert spaces, like sort of fiber over B, and the dimension of the representations gets multiplied by the dimensions of the fibers. Well, if this is supposed to be inducing one-dimensional representations to one-dimensional representations, it must have one-dimensional fibers. So let's call this module here X sub A, just so I don't have to write it down. So since XA induces one-dimensional reps to one-dimensional reps, it is the sections of a complex line bundle. It looks locally like the space times the complex plane, and the complex line is just acting fiber-wise. It just has to. And so what I've got is a bunch of vector bundles, which I can sort of paste together or glue together using the way that the AA stars and the BB stars and so forth overlap in this diagonal symmetry. So I've actually already got not only, okay, I expect there to be an obstruction, but I can already see where I would find the obstruction. In the data flow. Okay, and so the upshot is we can glue the XA together into a global bundle. I'll call it curly B over. Okay, over what? I said this was going to be something to do with groupoids. Right? There should be a groupoid here. Where do I get a groupoid in the picture that I'm looking at? Well, I've got a bunch of local dynamics. And this is one of the things that I kind of like about this approach. So one of the objections to the way that this is usually formulated is that there's not an actual inverse semigroup sitting around acting on it. But I've actually got an inverse semigroup available to me here. So maybe I'll just write this down over here. So note, maybe under my bit about normalizes. So xn tensored with or xn tensored with xn in this picture is going to be isomorphism to x and n. It's just going to implement the multiplication of these elements. Isomorphism in terms of isomorphisms. What that tells me is that the isomorphism classes of these things. So I'm going to call this set n of t, normalized to t. The isomorphism classes of these modules that I can build is an inverse semigroup. So where does the inverse operation come from? Well, I just take the conjugate module, where I swap left and right actions around the way that I take the conjugate of scalar multiplication. So it's just the flip over that. Which unsurprisingly corresponds to just taking the adjoint of the n downstairs. Right? So I should say also xn star, the conjugate module, is isomorphic to x n star, the module that I get from just taking the adjoint of n. All right, so what have I got here? I've got an inverse semigroup acting on a space, right? Because I've got a homomorphism for each one, so I can build its groupoid of germs. So over the groupoid of germs for the xn's. And now, and I'm just going to stop here. I'm going to state something and then I'm going to stop. So now the upshot is, and this again, as I said, not my theorem, although I'm not aware of this particular picture of it having been written down anywhere before. I think it's not known, but I'm not sure if it's been. It's usually written in terms of polar decompositions and so forth, because that was the technology that was available at the time. So this is a rephrasing of how to get at it. But the theorem, and I'm going to put a few names here. So I'm going to say Renault. So I know proved the theorem that I'm about to state, but I'm also going to just list Kunjan's name, because really Renault was building on the fundamental idea, the really crucial idea that makes this work for C-star algebras is the line bundle picture there, like the idea of a something like a line bundle or a twist. And it was Alex, I think, who saw that that was what was needed, not just a cocycle. And I'll also write down Feldman and Moore. I think there's only one in there. Because they really did this first for von Neumann algebras. But for von Neumann algebras, everything is Borel, so you can always choose lots of sections and you don't have to worry about what Kunjan had to come up with. So I'll put those three names there, but it's really Renault's theorem that I'm going to state. So the idea is if A is a C-star algebra and the subset of A is Cartan, shopping list of conditions that are needed here, and I'm not going to say what they. It won't help to say much, but Anna already told us basically what we want, right? So I'm pretty off Anna. So it satisfies the conditions that Anna mentioned. Then AD, this pair of C-star algebras, is isomorphic to the C-star algebra as Anna described it, reduced C-star algebra, of the groupoid of germs of this inverse semigroup action, twisted by this bundle that I get by gluing together all of these all these one-dimensional line bundles coming from the normalizers. And so we really do have a picture that looks like this, right? I've got a groupoid, which means I've got a topological space. It's an Natal groupoid, so a topological space of units. Locally, the groupoid is acting by these local homeomorphisms. There's a little bit of cohomological data thrown in, which we just can't get away from. But basically, every time I can find a Cartan subalgebra like this, I can describe my C-star algebra in terms of coordinates, in terms of a picture, which I can use to get my hands on it. Which also means, you know, basically any theorem that we have that says things about twisted groupoid C-star algebras is a theorem about any C-star algebra that has a Cartan subalgebra in it. And that's really one of the most powerful parts of the whole theory.
Because you wrote D on the left, you might also write C not of D in hat on the right.
I'm sorry, where am I?
You have a pair AD on the left.
Yep.
As morphic to a C-star algebra, one pair of C-star.
Oh, I'm sorry. Yeah, right. So, sorry. Yes, this should be. You're right. This should be C0 of D hat.
The B is still necessary.
The B is sort of hidden somewhere in there. So this is really. Yeah, sorry. I see what you're saying. So I need the B, and then I should have my C0 of. That's right. Thank you. Yeah. Yeah. So I need to keep track of the diagonal subalgebra. Is what I understand. But yeah. Okay, so I guess if you take one thing away from all of this ranting, it's basically this picture here. Right? So a C-star algebra that has a Cartan subalgebra really does look like this picture. And this is the spectrum of the Cartan subalgebra. And I haven't really talked about it, but also the fact that all of this fits into the falls under the rubric that Bavarian was talking about. A lot of this stuff you can do for abstract algebras. So there are huge classes of, there's a few different takes on them, but there are fairly general hypotheses on an abelian subalgebra of an abstract algebra that tell you that you can realize that abstract algebra as the algebra coming from the groupoid acting on a totally disconnected space by a stone duality base. So you replace the Gelfand-Nymak duality here with stone duality, and then everything else sort of try and follow it through. That's all I wanted to say.
Questions?
Maybe so. I'm just a little bit confused about these C-star algebras. They're C-star algebra of A star A is A star. The Gelfand spectrum is the spectrum of A, the real spectrum, right?
Yeah.
Those are not the same, right? They differ at 0.
Yeah. I'm cheating a little bit. I'm cheating a little bit because when I say C star of A star A, I don't actually. Usually, when we say that, we mean the C-star algebra generated by that and 1. But I'm not doing that for a start.
So it's functions vanishing at 0.
Functions vanishing at 0, unless it turns out that that's right. So yeah, I was fudging. Yeah, you're right. And of course, the thing is that you're sort of patching these. I mean, maybe A is an isometry, right? So the spectrum of A star A and the spectrum of A star are just points. Here's points, but they correspond then to, I guess, Clopen subsets of this big D, right? I mean, there's all sorts of gluing and stitching together going on.
It's like it's a pointed.
Yeah, because when you first look at it, it sort of feels scary. It feels like it says that the spectrum of D just looks like, locally like the spectrum of a self-adjoint thing. Well, it can't, right? Not everything looks like a one-dimensional, but yeah. Thanks. Yes.
Just checking. So in the middle here, we ended up with A and B.
Yep.
And on the right, it just coincidence be that that's actually completely differently on the far right.
Oh yeah, I'm sorry. Yeah, curly. Yeah, sorry. This is supposed to be a math cal B. That's supposed to be one. It's usually just written B for bundle. That's what I understand. I should use curly on the one.
That's just
Since I'm up here, can I just thank the hard work of the people who organised today and for inviting us here and giving us the opportunity to talk about the same. it.